Okay, gang, so here's a short presentation of the stuff that we're going to cover in section 14.5. And we'll break it up into two parts. The first part will be cylindrical coordinate system, and the other part will be the spherical coordinate system. So, and who cares? What we're going to find is that just like how in section 14.4 polar coordinates greatly reduced some of the problems that we had to do based on what the regions look like, cylindrical and spherical coordinates can do the same thing for triple integrals. Cylindrical coordinates simply put, the cylindrical coordinates are the polar coordinates in the xy plane. You know, you remember the equations, right? X equals r cosine theta, y equals r sine theta, and so on, with the z dimension added, okay? So think about it like this. Okay, so you have your regular, your polar coordinates r and theta, and the z dimension added, okay? So if you look right here, notice in the xy plane, we've got the regular r and theta, right? Those are the polar coordinates that we remember from our calculus 2 days, right? And the equations that relate all of the variables are these. Okay. Remember also, right, we know that when we square these two equations, add them together to eliminate the parameter theta, we come up with x squared plus y squared is equal to r squared. Okay, so it's kind of business as usual, but as we'll see in the next couple of examples, this will help us when we're solving triple integrals, okay? Now here, what I want to do is I want to draw a typical cylindrical block, we call it. Not a perfect rectangular box. It's going to be a cylindrical block. So something like this. Now, it's not a perfect rectangular box. Otherwise, its volume would be length times width times height. But we'll say, well, it's infinitesimally small, right? It's a differential element of volume. We've talked about these kind of things before. If you think about it like that, it's practically a rectangle. If we can find its dimensions, then we can find its volume. Okay. Well, according to the polar coordinates, this angle right here should be d theta, right? Remember, these are infinitesimally small elements. Okay, this right here, that would be the height of the box, dz. Okay. Again, do you remember in section 14.4 what this piece right here was called? We called that a polar rectangle. Remember? That's a polar rectangle. Its area was this. Okay, that was the area of that polar rectangle. So this this cylindrical box will have the same base, right? This box casts this shadow onto the xy plane. So that means the base of this blue cylindrical block is going to have the same area. So therefore, the volume of this block should be the area of the base times its height. And so we say the differential element of volume for this shape Now, if you think of this block as making up an entire three-dimensional solid, right? So that whole solid then would be made up of an infinite amount of these tiny little cylindrical pieces. So the overall volume then would be equal to this. Okay, regular triple integral because it's three-dimensional now. And we're using three different differentials, so I need a triple integral for that. And our integral would wind up looking like this. Okay? Now we'll see some examples of this in a couple minutes, and then after this we'll do the cylindrical or the spherical coordinates.